So number 40 from the book, there's an enzyme catalyzed reaction that has been carried out in a phosphate buffer, 0.03 molar, pH 7.2. But after reaction, there is an acid being formed at 0.004 mole per liters. So the questions ask you to calculate the final pH. So let's imagine and break these questions apart. So first, let's imagine that before you let the reaction occur, there's a beaker containing the phosphate buffer, pH 7.2, right? So at pH 7.2, you have to think that in the process of the phosphoric acid that being protonate, the pH 7.2 that's actually equal to the second pKa of the phosphoric acid. So before the reaction, the pH of the buffer is pH 7.2, and when you see the process of the protonation of phosphoric acid, the pH actually equal to the second pKa here, 7.2, or almost equal. So if the pH equal pKa, what does it mean? So it means that at pH 7.2 here, your solution would contain half of the acid and half of the base. So by half, it would refer to like 0.5 equivalence here, or 50%. So if your phosphate buffer, the concentration is 0.03 molar, so it means that your H2PO4 would have the concentration of 0.5 times by 0.03 molar, similar to your base species here, HPO4 2 minus. The concentration will be equal 0.5 times by 0.03 molar. So that equal 0.15 molar for each. So this is the concentration of the H2PO4 minus and HPO4 2 minus at pH 7.2. So if the pH of the buffer is not equal to pKa, what can you do to calculate the concentration of each species here? So you have to use the Henderson-Hasselbalch equation and solve for the concentration of the each species. So now you know that the initial phosphate buffer, the buffer contains H2PO4 minus at 0.15 molar and contain HPO4 2 minus 0.15 molar. So next part of the equation, we're talking about the enzyme catalyzed reaction. Anyway, when you let this reaction occur, as a result, there is a acid being formed in the solutions. So what does that mean? So you have proton being formed in the buffer is still the same system, right? It still contains H2PO4 minus and HPO4 2 minus. So what will happen with the proton that being newly synthesized here? So the proton, because it's a proton, which molecule of the buffer would proton bind to? So of course, the proton will bind to the base, right? And then it will change to acid. So because the proton will bind to the base, and then it will change back to the acid form here. So as you follow me so far, would imagine that at equilibrium after the reaction occur, the ratio between the H2PO4 and HPO4 minus would not be the same, and that make the pH change. To give you more in detail, in depth, here I would use the ice table to explain. So proton will bind to HPO4 minus, and since in the initial line here, you would feel the line with the concentration of the initial concentration before the reaction occur, which here we got 0.15 molar. I'm sorry, I got the calculation wrong here. It should be 0.015 molar, right? And 0.015 molar here because we use 0.03 molar times by 0.5. Sorry for that. So, okay, you feel the initial concentration that you have before the reaction. So for HPO4 minus is would be 0.015, and H2PO4 minus is also 0.015 molar here. But since you have proton being formed from the reaction, and the amount of proton is actually 0.004 molar, so it means that you have to plug in 0.04 molar over here. So because proton will bind to the one equivalence of proton will bind to one equivalence of HPO4 minus. So proton here would be the limiting substance. So it will bind the same amount of HPO4 minus here, 0.004 molar. And because this side is the substrate, so you have to minus the amount that have been changed, while the side of the product, you have to add addition to the amount that has changed. So one equivalence of proton bind to one equivalence of HPO4 minus, and then it is create one equivalence of H2PO4 minus. And you have to add it to the initial concentration for the product part. So that means that at equilibrium, your HPO4 minus concentration will be decreased and is equal to 0.01 0.011. Why the concentration of H2PO4 minus will be increased to 0.019 molar. And what you see here is the concentration of HPO4 minus and H2PO4 minus at equilibrium, and you need to use this value to calculate the final pH. So you can use the Henderson-Hasselbalch equations to calculate for the final pH over here. So pH equal pKa plus log B over A. So B will be H2PO4, sorry, your B would be HPO4 minus, while A is H2PO4. So use the Henderson-Hasselbalch equation to calculate the new pH here. So the pKa that we use in this equation would still be 7.2 to 1 or 2, yeah, because it's the most closest that what we are talking about. And then plus log B would be 0.011 divided by 0.019. And yeah, this will be your final pH after the reaction occurs. So I would like to point something from these questions. Is actually like a shortcut equations that we can use instead of doing this kind of the full work over here. So it's actually the modified version of the Henderson-Hasselbalch that we learned from class. So since our Henderson-Hasselbalch equation look like this, pH equal pKa plus log B over A. So if you run the reaction and at the end you have acid being formed, we already talked that when acid is being formed, it will bind to the base and then it's changed back to acid. So actually, you can appreciate that if your proton is being formed, it will bind to the base. So in other words, it will bind to the base and it's changed to acid. So that's why it will decrease the amount of base in your buffer. Whereas it eventually increase the amount of acid in your buffer. So you can have this modified Henderson-Hasselbalch equation, and then you can use these equations to calculate the final pH. But before that, don't forget to come up with the initial concentration of each of the basic species and acid species. So your pH will be equal 7.21 from pKa, and then log. What you will plug in here is the concentration before the reaction. So it would be the concentration of HPO4 to minus. So it is 0.015 minus 0.004 divided by 0.015 plus 0.004 here. So you can see that it's actually the same as what we got over here, right? So that is another method that you can calculate the final pH of these solutions. Again, these equations is only used when you have acid being formed after you let the reaction occur. Pay attention to the minus and plus sign over here, because if you run the reaction and there's a hydroxide ion being formed or the proton is consumed, it will be different from this equation. And it will just swap the minus and plus sign into the denominator and numerator. And I will explain more on the next questions, because number 41 from the book will talk about the reaction that you consume the proton. after you let the reaction occurs.